Hey everybody, okay, we are going to continue where we left off in the last lecture. We're still following this structure of the kind of relearning and reviewing the certain reactions from organic chemistry in the context of pharmaceutical chemistry. So, we're still on number 3, reactions of kind of synthesis of alcohols and ethers, for the most part, Grignard reaction and stuff. And we started talking about tamoxifen. Z-tamoxifen, we reviewed what that means in terms of the structure, being zusammen, or together. And at the end we mentioned that it's not very active itself as a molecule, as a ligand, of ER, and in order to be pharmacologically active it needs to be metabolized, and what we said was the word for that is called Prodrug. It is a Prodrug. Okay, so that basically means that the molecule has to be metabolized or oxidized or something in order to be biologically active. So let's just draw that reaction. So you got 2 ethyl groups. We got our phenyl, and the phenyl with the ether on it. We got a phenyl up top here. We got ethyl group here. Okay, so the enzymes that do this kind of oxidation chemistry are called or isoforms of Cytochrome P450. Isoforms, so they're variations of this protein, and they all kind of do different oxidative or hydrolytic reactions. We'll talk extensively about Cytochrome P450 later in the course. They're usually located in the liver, and if you consume this drug orally, it passes through the liver, and then the oxidation actually occurs. And the oxidation will be of this bottom left phenyl. It'll make a 4-hydroxy derivative of it. So let's try that. That's a weird benzene. Sorry. Okay, I got the ether up top there, and now we have a 4-hydroxy. Whoops, 4-hydroxy, not 3-hydroxy. Benzene. Okay, and so this is important now for binding to the ligand receptor. This stuff is the estrogen receptor. So this is Z-tamoxifen. This is called Z4OH. Hydroxy tamoxifen. Okay, cool. Now, I mentioned, whoa, sorry. There we go. I mentioned that the P450 has different isoforms, and they are identified usually for different reactions. We can identify which isoform is the correct one. And for this reaction, we call them CYP, 2B6 and 2C9. And other ones also, but they can actually identify them as specific variations of the protein. So this reference for this for this reaction is clinical experiments in pharmacological physiology. If you want to read more about this, 2003, 845, 848. Cool. Okay. Alright, and what I was mentioning, I think, at the end of class is that if there's other molecules maybe in your system that might suppress this reaction, that would kind of decrease the effectiveness of tamoxifen as a breast cancer drug. And that's actually that's been characterized, so let's talk about that next. Okay, so the reaction we're talking about is essentially Z-TAM for tamoxifen being converted to Z4-hydroxy-TAM. And this is done, for example, by Cytochrome P450 isoform 2C9. And one of the drugs that suppresses this, inhibits this enzyme, this metabolic enzyme, is Mycotazole, which is one of the early drugs we talked about in this course as an antifungal drug. I'll redraw it real quick. Mycotazole is chloro, ether, chloro, okay, that's Mycotazole. It was that thing that inhibited the growth of the fungal cell membrane, right? But anyway, so if you take Mycotazole, it can affect the, it can inhibit this enzyme. That happens frequently and causes drug interactions. Another thing that can happen with this, and of course this inhibits ER, the estrogen receptor, which is basically when the estrogen receptor is overly active, it basically causes uncontrolled cell growth and causes breast cancer. So ER has been a drug target for breast cancer for a long time. But there's other enzyme or other compounds, other drugs that don't necessarily inhibit cytochrome P2C9, but might act as a substrate for it, right? So, like, say there's another drug that's a competitive substrate. So it's being metabolized also by this enzyme, and then it kind of blocks this from being metabolized, right? And then it also will kind of have the same effect of not producing the active molecule. So that's actually a problem. That's actually that's the other problem. So antidepressants do this. So also some antidepressant drugs compete for the cytochrome, for CYPs, we'll just say, Cytochrome P450 isoforms. So it's not an inhibitor as such, but it's a competitive substrate. And that kind of affect the activity of a drug like tamoxifen. I think the specific examples of this are fluoxetine, which is Prozac, one of the common SSRI antidepressants, and sertraline, which is Zoloft, also used as an antidepressant. I think it's also an SSRI. I'm not 100% sure on that one. Zoloft. Okay, so anyway, that's kind of an interesting thing about this, about tamoxifen. The other interesting thing, I think, is that the molecule, and I'm not going to redraw it, is, you know, we saw it, is that alkene with a couple phenols and ethyl and everything like that. How it actually acts like a steroid, because it doesn't look like a steroid at all. I think that's pretty amazing as an organic chemist, that it would bind to the same receptor. So I'm just going to say it's crazy, I think, that the tamoxifen, or, well, actually 4-hydroxy-Z-tamoxifen, 4-OH-Z-TAM, it's pretty crazy that it is a competitive ligand and it, you know, it acts as an inhibitor in the breast tissue for ER when the normal natural steroid hormone it looks like this. Like estradiol, as an example. So it's so basically that molecule with the alkene kind of emulates this structure, which is, you know, it just shows that how weird organic molecules can fold and kind of adopt their structure to fit into a receptor like that. And this also shows with estradiol, it also has this hydroxy group that seems to be required for tamoxifen. So that kind of makes sense now, right? That it needs to be oxidized in vivo to emulate this structure, and that's where I think that hydroxy group seems to kind of emulate this hydroxy group. Okay, all right. Okay, so we're continuing this sort of theme of reviewing your organic chemistry knowledge to look at different pharmaceutical classes. We're still on this kind of alcohol ether Grignard section, which we're calling VS8 and VS9. And we're actually going to continue the theme of steroid type molecule, like, you know, we saw estradiol. But this time it's not going to be a hormone, it's going to be used as a totally different drug, as a diuretic drug. So this molecule is kind of interesting. It's called Spironolactone. It is a potassium-sparing diuretic. It's not a hormone, the way estradiol was. But it does have the general steroid skeleton that you're kind of used to. Okay, so what kind of diseases do diuretics treat, and what do diuretics do? They cause increased excretion of fluid, so usually increased urination. So increased urination, why would that be useful? I mean, in general, well, there's definitely a lot of diseases where you have fluid buildup, and you want to increase urination, and that helps treat the disease. The main use of diuretics is heart disease and heart failure that kind of have a buildup of fluid in your body. Generally speaking, we call that edema, which is swelling. Edema. Other diseases, hypertension, I think, is treated by diuretics sometimes. Some other diseases. Okay, so I'll show the biological cartoon of how these work in the kidney. What it does, though, as a drug, in a nutshell, is it inhibits sodium ion reabsorption in the kidney. And when it does that, when it inhibits sodium reabsorption, it basically fluid follows ions, and that as your fluids are transported through the kidney, if you inhibit sodium reabsorption, basically water will follow the sodium and will be excreted in urine. So this essentially increases water output, water excretion, and that's what a diuretic does. Okay, so it's one way to do this. Now, how is this a potassium-sparing diuretic drug? Well, with this molecule in particular, potassium, or K+, is actually reabsorbed. So while sodium reabsorption is inhibited, potassium reabsorption does actually get reabsorbed. So that's why it's potassium sparing, thus. Okay, so what are the effects of that? I mean, a big thing is you have more potassium in your body, and that can actually have side effects. So sometimes increased potassium can cause other issues. I think even like it can affect your heart and stuff. So that's a side effect, and that's kind of considered when diuretics are prescribed. That all said, usually when people are treated with diuretics, they're treated with a couple of diuretics, and they all kind of balance each other out, I guess. And this is one of those drugs. So it's usually used in addition to other diuretic drugs. Okay, so let's talk about the chemistry, and then I'll show a little bit on the biology of how these things work. I'm just going to go to new page, I guess. Okay. Alright, so we'll draw this molecule, and then we'll show how it's made. It's, even though it's a steroid, it's actually a relatively easy synthesis. Alright, so spironolactone molecule is a steroid. And steroids have this sort of six-member ring, 5-member ring, sorry, 6, 6, 6, and then 5 kind of structure. We have a methyl. I'm kind of ignoring stereochemistry here, just to make this simple. We got this little cyclic ester up here, 5-member ring. So make a little 5-member ring, 5, with the oxygen, and there we go. Alright, cool. And we got a little sulfur here. Okay, so that's spironolactone. What they're going to do is sort of build this little ester ring up top, and they're going to attach the sulfur thing. That's all they do, and this is all pretty easy chemistry. So they kind of attach that, I think, at the end, and then they build this little ring, little ester, and they also kind of attach this carbon piece. So there's going to be a CC bond forming reaction. What's the molecule called again? It's spironolactone. Spironolactone. Do you guys know what a lactone is? Have you heard of the word lactone? And do you know where that is in the molecule? It's kind of a weird word. You may have heard in your courses at some point. A lactone is a cyclic ester, and that looks like a cyclic ester, right? There's oxygen there in the ring. So that's the lactone portion of this. Lactone, which is a cyclic ester. And you probably have heard of lactam, like beta-lactam antibiotics. Lactams are cyclic amides. So when you have like a nitrogen there, then it's a lactam, and beta-lactam is just a 4-member ring lactam. So this is a 5-member ring lactone, gamma lactone, I think it's called. Anyway, yeah, there we go. That's spironolactone, and that's kind of how they're going to build it. Also, this thing is kind of a weird fragment. You haven't seen that really, probably not much before. It looks like an ester, right? Esters are C double bond O and like an oxygen, but this is a sulfur, so this is called a thioester. And that can be installed really easily, kind of through nucleophilic attack, so that the sulfur will just attack an electrophilic carbon. We'll show that in a second. Okay, so that's what we got to make. How do they do it? What's the kind of the standard synthesis of this drug, this diuretic? So I'm gonna kind of go up top and sort of just step through this all, and it's only a couple steps though. All right, so we're going to start from a different steroid. That's pretty cheap. A steroid building block. So make our little 6, 6, 6, and 5. Methyl, ketone, alcohol here, and a methyl there. And I just realized I screwed up. There's an extra methyl down here in the product. So you have a methyl right there. In this, that is that point. Okay, so methyl and methyl. There's 2 methyls. Methyl, 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 and methyl. Okay? Alright. Cool. Okay, so they're going to basically try to build this little cyclic ester thing off the ketone. And the way they do that is pretty clever. It's cool. So they essentially they start with this alkyne, like that, and then they react it with a base, B dot dot, a base. And the base, remember with alkynes, you may have forgotten this from your organic days, but alkynes, the proton there at the end is kind of acidic. It's low pKa, it's like 20 or something like that. So if you use the right base, you can take off that proton, and then you make a alkynyl anion. It's like a C dot dot minus alkyne, and then you have the alkyne. It's a C triple bond C, right? Cool. Now that base is probably going to take off that proton also, so it does that too, as O minus. But that oxygen doesn't really, the carbon's more nucleophilic, so the carbon's going to actually go attack, and the oxygen just kind of goes along for the ride, even though it does get deprotonated. So the base probably takes off that, it probably takes off that, and you get this O minus thing, okay? Okay. I guess also it's kind of cool that they didn't protect the alcohol, because we learn in organic chemistry that kind of if you have two reactive functional groups, that maybe you protect the one you don't want to use. Because what they're going to do is have this attack the ketone. It's a pretty simple reaction. It's a negative charge attacks the ketone, which has a positive charge, right? Or a partial positive charge. So the ketone, of course, is a delta minus, delta plus. So that delta plus is on the carbon, I guess, right? So the carbon's delta plus, the oxygen is delta minus. So this negative attacks the ketone, kind of like a Grignard would, right? So it just kind of goes in and attacks, right? And it forms a CC bond. C minus attacks the carbon, pushes electrons up. It's cool. C minus attacks delta plus, and kind of like a Grignard does. But the carbon's more nucleophilic, so the oxygen doesn't do the reaction, and that's actually kind of cool because you know we can avoid protecting. It's like this is a case where we're avoiding protecting the oxygen, and it's totally okay because this doesn't do anything bad. That's kind of cool. You're probably, you know, from your organic days, you're probably used to, you know, you always protect the second functional group. This is a case where they don't. Alright, so then step 2 is the water, whatever, and that just will protonate the oxygen. So what do we got now? And the other, yeah, actually, and there's also this alcohol, but that doesn't cause any problems. So they don't protect this either. Okay, but anyway, all we're doing is attaching carbon to carbon. And what do we have now? A new steroid. Got our steroid. Let's start with those methyls. Don't forget the methyls. We got our alkene and the hydroxy group over here. Alkene, hydroxy group over there. All right. What else? Now we have an alcohol. And now we have our alkene. Make sure you draw the alkene kind of linear, because alkenes are a linear functional group. And we got our alcohol there. So that's cool. That was pretty easy. All we did is attack the nucleophile onto the ketone. Now we have an alcohol with the alkyne and a hydroxy group. Okay. Interestingly, the next step is H2 and palladium on carbon, and what this does is it reduces the alkyne, because H2, palladium, and carbon, this is a reaction from organic 1. I think organic 1, maybe we teach it in organic 2. But essentially it reduces an alkyne to an alkane, so it goes from a triple bond to a single bond. Interestingly, it doesn't do it to that alkene there. That's probably because it's in the ring and it's a little less reactive. Whereas this guy is kind of out in the open and it just sort of is maybe more reactive. A little surprising that the H2 palladium doesn't touch this alkene, but that's the case. And then they're also going to, I'm just going to sneak in an extra step here, chromium trioxide, CrO3. This is an oxidizing agent. And that's going to oxidize the alcohol to a carboxylic acid. And that's also kind of a reactive alcohol because it's kind of poking out in the open. And that's why I think it doesn't react with this. Actually, no, it does. It does. Yeah, it actually oxidizes two things here. It oxidizes that to a carboxylic acid, and it oxidizes this to a ketone. So we're getting, this actually is doing two oxidations. All right, carboxylic acid, ketone. Let's try that. Okay, so we got our new steroid. We got our methyls. We got our alkene here. That alkene sort of survived the hydrogenation. And we got our ketone there. Okay. And now, like I said, we still have our alcohol here. But now we have carbon, 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 and then carbon, carbon, then the carboxylic acid. So carbon, carbon, and then our carboxylic acid. We'll just sneak in there and draw that. Carbon, carbon, carboxylic acid. It's acetyl window OH. All right. Carbon, carbon, carboxylic acid. Okay. All right. So we're cool. That's all we did. We reduced the alkyne, and we oxidized 2 functional groups. All right. Now we treat those with acid, and this is actually kind of cool because remember how we have to make an ester? How the molecule, the final product has an ester functional group? Well, if you have an alcohol and a carboxylic acid, that will cyclize and form the ester. It's called the Fischer esterification reaction. So this actually will react with the carboxylic acid. It's a Fischer esterification. Esterification. Fischer esterification that builds the lactone, the cyclic ester. So that essentially, the mechanism is all organic too, but essentially you're making OH a good leaving group, and then hydroxy kicks it off, breaks it off, and that builds the ring, the little 5-member ring. Okay. This also it moves the alkene to be next door to the ketone. It's called isomerization. So the alkene is a little less happy there. It's a little happier when it's next to the ketone because it's conjugated. So less happy, more happy. So it also happens. So there's 2 things that happen. Make lactone, the cyclic ester, and it also isomerizes the alkene. Isomerize just means move. In this case, alkene moves to alkene. So those are the 2 things that happen. All right, so what do we got now? Steroid. Steroid. Now we got our ketone, and we have our isomerized alkenes. So the alkenes down there. 2 methyls. Okay, now we have our little ester, the cyclic ester thing, which I have to erase these words to fit it in. So I'm going to erase the words isomerized alkene. Just squeeze it in. Okay, so we'll sneak in that cyclic ester now, the 5-member ring ester. There's our little 5-member ring. Okay. All right, so we're almost done with the synthesis. Last thing we really got to do is get that sulfur thing in. They do something I'm not going to talk about just because it's a little beyond your level, but I'll just have a couple arrows. It essentially introduces another alkene. So let's draw that. I'm just going to draw the product. I'm going to say steps. So this is a little bit of advanced chemistry. But all they're doing is adding a second alkene. methyl, ester. Let's draw this. The best way to draw this little guy is draw a little 5-member ring. 5-member ring. Oxygen. There it is. Alright. That's that little 5-member ring. Cyclic ester thing. Okay, and then we have, after this little step, we got our ketone. We have 1 alkene, 2 alkene. Alright? So that's where we are now. The last step is actually really easy to make the product. So I'm just going to square the final product here. That's what we're making. And they just essentially do this thing, Mycol reaction, which is what a thing you learned in Organic 2, which essentially attaches this sulfur thing right there. And I'm going to draw the mechanism. It's really easy though. How it differs from your organic knowledge is that usually when you do a Mycol reaction, it's called Mycol reaction. Mycol. You usually do a Mycol reaction when you have an alkene next to a ketone like this. So like this would attack there and then kind of push the electrons towards the ketone. This is a special Mycol because you have a second alkene, and that's what's required to essentially put the sulfur where you want it. So a little different from your Organic 2 knowledge, but it's really not that bad. All we do is, the mechanism is super easy. It just attacks that carbon right where we want it, right? Right where we want it. Right where we want it. And then this kind of goes there. This goes there. A couple arrows. And then in the end, the electron, after you do a workup or something, the electrons go back, and then you get your final product. But that's essentially how this sulfur thing goes right where they need it. They add this extra alkene, have it attack, and then there we go. So that's spironolactone. It's well, it's related to what you know. There's a couple little tricks. It's cool that we're doing multiple step synthesis on a steroid here to essentially make this amazingly biologically active potassium-sparing diuretic drug. Okay? Alright. That's it for the synthesis of this one. Okay, so I'm going to show a little bit of PowerPoint stuff, and find that it helps me with my video editing if I just point the camcorder or the monitor. So we're going to try this time. How do diuretics work? They target a system called the Nephron. It's part of the system that the kidney uses to filter blood and kind of reabsorb ions and nutrients and things like that. So they don't all get excreted, but diuretics sort of affect that system, and that's pretty much how we can cause increased urine production. All right. Okay, so this sort of shows the overall structure or how the nephron works. It kind of goes from left to right. It's this kind of weird filtration system. And yeah, it's called the nephron. There's about 1 million nephrons in the kidney, so it's sort of a repeating subunit. And essentially what happens is blood gets sort of filtered through this thing on the left. It's called the glomerulus. I have the spelling of it on the next slide. And it kind of goes from left to right. And kind of along the way, as blood and fluid gets pushed through this system, various ions and things are amino acids and things like that, are transported back into the system. Okay, and we're basically trying to reuptake different things and ions and potassium, sodium chloride, water, amino acids, and things like that. There's this little loop. This is called the loop of Henle, and certain diuretics operate specifically at the loop of Henle. And then we kind of go into this ascending loop. There's more of these transport mechanisms, and eventually there's also this thing called the aldosterone receptor, which we'll talk about. That's really the target of spironolactone. The steroid we're discussing. Eventually, fluid is excreted at the right side in the output portal, and that's basically what becomes urine. Okay. There's also something called the Antidiuretic Hormone Adh, and that also it's the opposite of a diuretic. It causes water to be reabsorbed, right? And so this kind of prevents diuretic action, right? And it kind of keeps water in our system. And this is kind of how we, like, if you need to urinate, your brain, it basically can turn off antidiuretic hormone, and that allows the system to excrete more urine. So it's kind of like a feedback mechanism, right? Okay, so anyway, so this just shows the input portal again, the glomerulus, which is where this kind of attaches to circulating blood. And then at the end we have our output material excreted as urine. Alright. Okay, so then the diuretic drugs, and there's different classes of diuretic drugs. There's the loop diuretics, like furosemide, that kind of operate in this loop of Henle region, and it prevents uptake of things like magnesium and calcium, and that causes more liquid to be excreted, right? There's the proximal part, and thiazides kind of operate in this region of the nephron, thiazide diuretics. And then our molecule of interest, spironolactone, operates on the aldosterone receptor, and we'll show how that works. And kind of an interesting thing is, this doesn't look like a normal drug because it's a steroid, but it does operate on the aldosterone receptor, and aldosterone is a steroid, and so we'll see some similarities between the two structures. Okay. Anyway, that's one way to kind of see how diuretics work. The original figure is on the website. This is an alternate depiction of the nephron and how diuretics work also, and I have a couple of notes that I'll display in a second. Okay. So this shows the glomerulus, blood gets basically filtered in, and then you have this mixture of fluid with different ions, and then there's a series of tubules which kind of cause reabsorption of materials, amino acids and ions and things like that. And then the loop diuretics work kind of in the early stage of the nephron, or this sort of ascending region. Thiazides work a little bit later and cause block sodium chloride reabsorption, which will again cause more net fluid excretion. And then aldosterone is basically a sodium potassium transporter, and we'll talk about that in a little bit. And aldosterone antagonists block aldosterone, and that basically will cause potassium to be spared and sodium to not be spared, and sodium will basically get excreted and then bring water along with it, and that's how a diuretic works, right? And then eventually the liquid gets excreted out the collecting duct, electrolytes and other things get excreted, eliminated as urine. Okay, so one of my little notes here, this just kind of reiterates what I just said. Let's see if I can zoom out. You have the slides. Okay, first thing, when blood is filtered in the glomerulus, sodium, potassium chloride, and other substances are filtered into the tubule. The tubule is the nephron. Filtered substances then move through the tubules towards the collecting duct into the urinary tract. Along the way, sodium, potassium, and chloride are reabsorbed into the tubule. Diuretic drugs block the reabsorption of the different sites along the tubule. Often cocktails of diuretic drugs you have a net diuretic effect. So they all have kind of side effects, and if you sort of mix and match with the diuretic drugs, the side effects kind of get decreased. That's the idea. Water tends to go where the ions go, right? So if we block the reabsorption, it causes more fluid to remain in the tubule. Ultimately, more fluid gets eliminated as urine. Okay, so now we basically have an idea of how this, how the nephron works, and how diuretics that target the nephron work as well. Okay, so one thing I want to mention about spironolactone again is that it's sort of a weird structure compared to the other steroid structure. Compared to the other diuretics that we mentioned, like the loop diuretics, like furosemide, and also the thiazides, which is a little later in the nephron, thiazides. And we mentioned that the reason is because spironolactone inhibits the aldosterone receptor. So let's just show the structure of spironolactone versus aldosterone. It's kind of a fun thing, and you can see that, you know, they're both steroids, and that explains the activity of spironolactone. So, like I said, spironolactone blocks the aldosterone receptor. We'll mention again what it does in a second. Spironolactone is this steroid. A thioester, which is kind of a random weird thing in a molecule in a drug. Oops. Okay. All right. And it kind of, I mean, it has some structural similarity to aldosterone, which is another steroid. It does not have the lactone. It does have the two, oh, actually, interestingly, it doesn't have the second methyl, it's an aldehyde up here. Has an aldehyde up there, and it actually has a ketone, an alpha hydroxy ketone. So it's different. There's some differences. Yeah. It's got this methyl. It's got this alkene, and it's got the ketone. So those are some similarities. The alkene of the ketone, alkene of the ketone. It does not have the thioester. So it's just kind of oh, it's got a hydroxy group too. It's, you know, it's always a little bit weird how this molecule has we can actually block receptor binding of the natural ligand, aldosterone. Even though the structures aren't they have some big differences, right? Hydroxy group, aldehyde, a ketone in an alcohol versus a cyclic ester. All that's kind of weird. And this random little fragment, the thioester. So that's kind of weird. Okay, so what does this do? What does aldosterone do again? It's the natural ligand of the aldosterone receptor. And what it does again is it increases sodium absorption. When aldosterone binds, it increases sodium absorption, and it increases potassium secretion. So it's like an exchanger protein, channel protein. And anyway, so then what this does is it blocks that, right? And the net effect then is that sodium is actually secreted and potassium is preserved, and thus it's a potassium-sparing diuretic, which is pretty cool. It's nice that this mechanism is pretty well characterized, and the net effect is more fluid is excreted, and then but potassium is spared. Okay. All right. Slowly wrapping up. We have a couple more things we want to talk about. We're still moving to another drug now. This whole general topic has been alcohols, and really maybe we've seen oxidation and things like that. I'm going to mention one that we saw before. We talked about stereochemistry last week. Meprazole, remember that one? So this is kind of an interesting example of oxidation, but not of alcohols. Meprazole was the weird sulfoxide thing. Remember the chiral sulfoxides? And how we had a weird sulfur chiral center. Well, let's just mention this because it's an easy molecule to synthesize. It's a proton pump inhibitor. Proton pump inhibitor, which is used for like heartburn and gastroesophageal reflux disorder, GERD. So heartburn, GERD is that sort of general kind of like reflux in your digestive tract and your esophagus. And anyway, so how do they make this? It was I'll draw the molecule. I'll show the synthesis. It's pretty straightforward. This is an easy one. It's just one step, or two steps, I guess. Alright, so methoxy, draw the product below, and then the synthesis above. Okay, so then we have sulfur. Here's the sulfoxide. That can be, it's a chiral center, right? And I'm just going to draw this kind of as an aromatic ring with the methoxy at the top there. Okay, and so they build this essentially. We'll see from they can build that carbon bond, essentially attach the left piece and the right piece together, and then they just oxidize the sulfur. It's actually a pretty simple little synthesis. All right, so they start with a thiol, which is just like a sulfur-based alcohol type thing, almost, right? So they start with the left piece, methoxy, and they have a little nitrogen and a nitrogen, right? That's called a thiol. Like a sulfur-based alcohol, right? A thiol. And they just react this with a base, and then an alkyl halide. And the alkyl halide is simply nitrogen, methyl, O-methoxy. Alright, so it's just an S&T reaction. Base takes the proton, make a good nucleophile. Nucleophile attacks, kicks off the chloride. Right, that's easy. And that is kind of like that ether synthesis we've seen a few times, the Williamson ether synthesis. Where this is actually making another functional group. O-methoxy, methoxy, and then we have nitrogen, NH, nitrogen. I'm gonna draw it down here. Okay, sorry. No space. If I had a whiteboard, this would be easier. Okay, so yeah, that attacks, and then we form the carbon-sulfur carbon linkage. Sulfur, carbon, methoxy. Okay, we cool? That's all we did. Base takes proton, S- attacks the carbon, kicks off the leaving group, the chloride. And then we have this. What's this functional group called? It is, that's a thiol. This is a sulfide. And this functional group, of course, is a sulfoxide. Okay, and the product's name is Meprazole. Okay, there's also something called a disulfide, which is carbon, sulfur, carbon, right? That's a disulfide. It's like a, I don't know, I've never heard monosulfide, but it is a single sulfide. Just reviewing organic chemistry. Do you know what it's called if it's a sulfur double bond O? Like if it's this? Because you'll see that from time to time. It's not a sulfoxide. Anybody know what it's called? It's a sulfone. Okay, so we just reviewed some of the naming for sulfur functional groups. Okay, so we got here. Now, what's the net thing we have to do here to finish this synthesis off? We just have to oxidize the sulfur. So you just have to use the right oxidizing agent. It's actually very simple. It's just H2O2. Sulfur, hydrogen peroxide is the nice oxidizing agent. H2O2 that does this, makes this. Okay, so going back to our stereochemistry discussion, would this be? We said that this is a chiral center, right? Sulfur is a chiral center. So we're going from an achiral molecule to a chiral molecule, yeah? That's chiral. It's chiral. So is this a mixture of stereoisomers, or I mean, it should be a mixture of the two, the R and the S, right? R omeprazole and S omeprazole. And what's that called? If you have a one-to-one mixture of stereoisomers, it's called racemic, right? So this makes the racemic mixture. Racemic, which means 50-50 R and S, right? And that's what meprazole is. It's the racemic mixture of the two stereoisomers. So, and then the question is, well, how can we possibly make? Because remember, there's also the S, the single stereoisomer S version of this, right? So let's draw that again. H, nitrogen, sulfur, double bond O, and then it had like the dash 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 lone pair thing. Just like the single stereoisomer, right? CH2, and then you got the nitrogen, blah blah blah, methyl OME, methoxy. So just make this very clear. It's a lone pair, yeah. Okay, and what was the name of this? It was a very clever name. That's a Meprazole. This is, the stereochemistry is S, right? If you do the chirality determination, it's S. So the name was esomeprazole. So they put that into the name. Meprazole. And there's all that controversy of, you know, whether the single stereoisomer is actually more efficacious or if it's just kind of a profit strategy. Well, now as a synthetic chemist, how could he possibly do this? This is actually kind of interesting, right? Because if H2O2 would make a mixture of R and S, like what could we possibly do that would give us a single stereoisomer, right, of omeprazole, right? That's an interesting question. One way you could do it is take this and separate the mixture, right? You could, that's hard. That's not easy. Taking a mixture of enantiomers, which is what this is, 50-50 mixture, and you can actually kind of separate the two and you get 50% of one, 50% of the other. Try to separate them. Sometimes you can do it with crystallization with a chiral reagent or tartaric acid, or I don't know, something. It's called resolution. That word is, resolution means separation of enantiomers. Resolution is separation of enantiomers. Okay, so now this is actually, you know, what most of our chemistry has been stuff you know, but this is going to be something you absolutely do not know, but it's kind of fun. They don't resolve this. When the company, I think AstraZeneca, I think, when they make this, they actually make it as a single isomer. That's crazy, right? How could you possibly do that? How could you oxidize one face of the sulfide and not the other? Well, that's a whole area of chemistry. It's a whole area of synthesis. I'm going to erase the word sulfide here so I can draw the reagent. They do this with a special chemical. They actually add a special chiral reagent that will selectively oxidize this to give them one stereoisomer. And it's super cool that you can do this, and this is like, you know, the kind of stuff that wins Nobel Prizes nowadays, of like making single enantiomers. Okay, so they just to cut to the chase, they used titanium Tetra Isopropoxide. That sounds scary. I'll draw it. It's just titanium metal with 4 isopropoxides on it. I'll draw that in a second. Isopropoxide is like isopropyl alcohol without the H. And then they use something called SS det. S, S det, which is diethyl tartrate. It's a dirt cheap chemical that's based on tartaric acid. Tartaric acid is dirt cheap. It's chiral. That's what the S and S mean. And so this combination of reagents, this is a Lewis acid, this is a chiral molecule, dirt cheap, will selectively convert the sulfide, a chiral, into a single enantiomer of omeprazole. Okay. Let me just write the name of this concept. I'll zoom in there. So the name of this concept of we're making single enantiomers is called enantioselective chemistry. enantioselective because we're being selectively creating one enantiomer. Enantioselective means making a single enantiomer. Now, we're going to specifically just call this an enantioselective oxidation because it is an oxidation, right? Enantioselective oxidation. But there's a gazillion different enantioselective reactions, and that's a whole topic of advanced organic chemistry. If you take a synthesis course, you'll learn more about enantioselective reactions. Okay, so lastly, let's just draw what this is and what that is. I'm just going to sneak that down here. So this is very simple. Titanium, Tetra, Isopropoxide. It's just titanium, O, 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 O. And it's just like a Lewis acid. It's, titanium is a Lewis acid. Okay, then the fun is really the det, because that's the chiral reagent. So, and that's what causes the formation of a single enantiomer. So SS det, DET, diethyl tartrate. Is just a diethyl ester of tartaric acid. So, pretty simple molecule. That's what that is. Tartaric acid is simply this, the dicarboxylic acid, so OHOH. So this is the diethyl ester of it. And what happens is probably actually, I'm sorry, there's one more reagent I forgot. It's H2O. You need H2O2 in here also. So H2O2 is in the mixture. So it's really the combination of all these three things. This is an oxide. You still need the oxidizing agent H2O2. Okay, so it's titanium thing, H2O2, and SS det are all used for this. But anyway, so you know how this actually works is kind of complicated, and I'm not going to really get into that in this course. But this chiral molecule will kind of interact with the Lewis acid, and it creates this sort of chiral pocket almost that in the end will kind of allow only one face of the sulfide to react. So that's kind of how all enantioselective reactions work. So anyway, it's a little introduction to enantioselective chemistry for you. Lastly, I just looked up the cost of this. It's this stuff. You might think of a chiral reagent, a single enantiomer reagent like this might be expensive. It's not that expensive. It's 100 grams per for about $70, which is actually not that expensive. And the other thing is it's a catalyst, so it's not like we use very much of it. It's not like you would just add a little bit of this, like a 1 mole % or something, into the reaction, because it's a catalyst. That's kind of a cool feature of this reaction. Okay, the last thing I'll say here, just thinking as a organic chemist, and like you may do reactions like this at some point. They're making the S sulfoxide, right? S sulfoxide. What if you want to make the what's the opposite of S? R, right? What if you want to make the R sulfoxide? If you want to make the R sulfoxide instead of the S sulfoxide, how would you do it? Like, what would you do differently? It's very easy, but just think about it. What would you do differently if you want to make the enantiomer of this? Maybe you should use the enantiomer of SS, right? And that's right. So if you want to make the R a meprazole, you would use RR diethyl tartrate. right? It would be the enantiomer of this. So it would be, instead of dash, 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 it would be wedge and wedge. And that's also probably about the same cost, roughly 100 grams, $70 or something like that. So anyway, that's pretty cool. So we can make either one enantiomer or we can make the other enantiomer by just using the correct stereoisomer of this diethyl tartrate stuff. Okay, I think that's it for today. Hey everybody, I realized after I got home that I made a slight error on describing one of the drug targets in the Nephron. I just wanted to correct that real quick. I changed it in my notes, so I hopefully won't make this mistake again. But anyway, we talked about the nephron and how it's just kind of repeating subunit in the kidney that does filtration and reabsorption of ions and things like that. And kind of goes from the input side on the left, output side of concentrated urine on the right. And then the error I made was about furosemide, which is a loop diuretic that kind of interacts with the loop of Henle. I mistakenly said it interacts with magnesium and calcium reabsorption, but that's actually not correct. And it wouldn't make sense anyway because there's not very much of that compared to like sodium and potassium. So I double checked that and I was wrong. And so anyway, furosemide actually does inhibit reuptake of sodium chloride and also potassium chloride too. So two of the major ions that are being excreted. So and so when it inhibits the reuptake of them, then more sodium and chloride are released. So it's not the same as like the potassium sparing diuretic we were talking about. And anyway, that's what happens. Okay, so furosemide inhibits reabsorption of sodium chloride and also potassium chloride. All right, that's all I wanted to say.